Thank you very much for giving opportunity to present this lecture. And I will start to, I would like to overview actually the basics of detection. And the terahertz frequency range is a very specific one. So actually those principles are applicable actually to very different ranges of electromagnetic radiation. But then there will be some peculiarities which are really terahertz frequency range relevant. So if we can classify detectors or terahertz detectors, then this classification is large. And actually we have many phenomena which we can use to detect radiation. And the first one, I would start from direct detection like photon detectors. In this case, we respond directly to individual photons and which release bound charge. An example of such detectors could be photoconductors, photodiodes, semiconductor SAS junctions, and so on. Now, one of the biggest part or most used part is a thermal detection. In that case, we absorb photons and thermalize the energy, and change the energy into thermal excitation. And that example is a bolometer, Golay cells that are used like optoacoustic detectors, pyroelectric detectors, thermopiles, and a variety of all this family. And there is a very different way using electrical rectification. If radiation is taken directly to excite electrical current flow, and the nonlinearities of current voltage characteristics are exploited. That example is especially used in terahertz frequencies, like Schottky bar diodes, tunnel diodes. And since 2 decades, there is entry into this field by field-effect transistors. One thing, it's also not all phenomena, optical rectification, and then we respond to electrical field strength and, for example, electro-optic detectors. That's a family of devices which actually ignited this biggest scientific and technological interest in terahertz field range. So we actually, although for the longest range, those thermal detectors, photon detectors, and rectifiers have been used, that if you know, using femtosecond lasers and then exploiting optical rectifiers was the boost to the field, where then we entered back into other standard detection phenomena. So the outline of this lecture is such that I would like to give you an overview or explain the operation principles of thermal detectors, and the examples like bolometric, pyroelectric, and Golay cell. Then we'll go on to electrical rectifiers. I will try to give clear explanation of rectifying diodes, and very important field of my own research is rectification using field-effect transistors. And I would like to finish with quantum detectors, or what is needed to go to the most, what is needed to produce the most sensitive detection actually in terahertz frequency range. So let's start from the bolometer. So bolometers are based on an absorber which is linked to a heat sink. And then there are several ways how you can do so. In general, power is taken by absorber, then you heat, just impose a temperature changes on some specific heat mass, which is linked to the thermal reservoir with a thermal conductance. And that the question is only how to measure changes of the temperature. As an example, this resistive having a thermometer. So this is very special case, resistive thermometer. And in this very general case, bolometer detects any photon it absorbs. So it is not specific to to the wavelength, and the specificity is given by the material of absorber. What the mechanism is used, and sometimes absorber can be just direct absorption by material itself. Very often, like I will later show in bolometers, that's just carbon black or some external absorber is used, and then only silicon crystal or whatever other crystal is used just to measure temperature changes. So let's start from functional principle. Everything is, well, can be very simply understood by thermal balance equation. Need to shift my. So in the thermal balance equation, we have a change of temperature multiplied by heat capacity. Then we have thermal conductance to the change to temperature minus the temperature of the bath, and then the power which is applied. So with this thermal balance equation, we can calculate how the temperature change, what will be the temperature change for a step-like power excitation. We apply power, and then we will have that in this system, temperature will change. We can do the same like doing harmonic signal analysis and to find out what will be frequency modulation of the temperature, delta T on the frequency for those parameters if we apply oscillation in power. And once we add material which has temperature coefficient of, for example, resistance dRdt, and apply current, then we can measure, then we can change those temperature variations directly into voltage oscillation, into variations of voltages, which is measured. And one can have it as analogous to electrical circuit here. So those temperature variations are stable or steady at DC frequencies, and then with a time constant G over C rolls down at the frequency. And that's approximately electrical circuit, what we can do. How can we understand it? So what is very clear here, that if we have better higher thermal isolation or lower thermal conductance, then we will have higher change in the temperature. Only lower thermal conductance will change cutoff frequency or roll-off frequency of this temperature changes in the signal. So it is like defining the frequencies modulation bandwidth of your device. Now, one very important thing that, so if material has temperature dependence on resistance, and we would apply some current, then it might have, or not might have, but it usually has nonlinear IV characteristic, because then we apply additional voltage or current, we bring into different bias point, we heat material itself, and it sets to the steady state. So if it is now a DC character, not DC, but stationary characteristic, voltamperic characteristic of bolometric device, then it might look like it is shown here in a review of bolometers for infrared and millimeter waves by Paul Richards. It's a very nice article to read about operations of bolometers and actually various varieties of bolometers. So what is important that we might have like stationary resistance or a voltage over current ratio, or differential resistance, so the slope of the load curve. And once we have this bolometric sensor, we can measure its load curve, and then from the slope of it, we can, having its temperature coefficient of resistance, we can do rearrangement or really analysis of the change of delta of voltage to the current here, to find out that this allows us by from electrical characteristics to define what would be electric responsivity of that device. Since we apply change of the power in the terms of Joule heat directly in device, just scattering or just due to resistance of it, we can really very nicely relate it to the bias current, then differential or a slope of the load curve to the resistance of the device, just voltage over current ratio. So what is, this is kind of what we have with a bolometer devices, that we can calibrate them very well, or we can understand them very well where, what is the limit of performance or electrical responsivity of that device. Now, if you would like to identify what would be thermal sensitivity, it is also very nicely said by statistics. And one of it is just having that the power probability, actually fluctuations of the enthalpy. And from that, one can just find out that the temperature fluctuations, variance of the temperature, just based on the statistic of this device, is limited to the temperature and the Boltzmann constant and that thermal capacity, so thermal mass of a sensing system. So this allows actually very directly to find out what would be fluctuations in a standard deviation of a temperature and actually extract noise equivalent power of it. So just coming directly from statistic, from enthalpy fluctuations, we can get that NEP, noise equivalent power, of the smallest power, which creates variations equal to the just fluctuations of a temperature, inherent fluctuations of a temperature, just are expected, can be expressed by 4 kT square Ng, thermal conductance. This gives a very nice way to find where are the limits, even theoretical limits on NEP. So even we do not say what would be electrical responsivity, how good our thermometer would be, such system can show, well, would have its statistically limited noise equivalent power set just by the thermal link. And weaker this thermal link is, the better would be performance. And for example, or as a rule of thumb, at room temperature, one can easily get Gs of 10⁻⁵ watt per Kelvin. And we just tell us that such room temperature device might get 7 picowatt per square root hertz. Now, if we have better situation, vacuum, cool down, then we can get actually just limited by radiative heat loss, radiative heat transfer mechanism as it is done for state-of-the-art bolometers. So Gs are 10⁻⁹ or more, and this is where that bolometers have their limits down below picowatts per square root hertz. So what is the status of the state-of-the-art instruments? And probably you are very well accustomed to 2 companies which sells them commercially. That's QMC or Infrared Technologies. And what we usually cite or write that those bolometers typically have optical net and just commercial devices of few picowatts per square root hertz, but their electrical NEP, limited or measured by load curve and just coming out from responsivity and just from enthalpy fluctuation, actually is down into hundreds of femtowatts per square root hertz. So there is a huge difference, more than factor of 10, from what is electrically limited for that device to what you can get commercially. And the principle of bolometer is applied in very different applications. And that, for example, just the photos of 1 point here where thermal element or absorber is placed directly in the center here, and the spider web to limit thermal capacity, thermal link to the thermal bath. And the same thing can be done, you see, as small as a tip of a pencil here, and then a big array. So that's used for space missions. And for example, this is, well, those are requirements, and that what bolometers are actually applied there. So they are really cooled down below Kelvin, and can be actually very many pixels, up to 10 to 4 pixels to 25. So in these two different different array formats. Now, as a second very important phenomena, or very widely used phenomena, is a paraelectric effect. In a review of Lang here of paraelectricity, there is a statement that it is actually known by history for more than 2,000 years. And that's a little bit of a dispute here. Is that true or not? But actually it's actually almost from the times of Aristotle, not by him, by his successors. Properties of tourmaline, or probably properties of tourmaline, have been described, and that's one of the naturally known pyroelectric crystals, or not naturally known gems, which has pyroelectric properties. So what is important with pyroelectric phenomena? So it is just a creation of temporary voltage by response of the variations of temperature. So if the temperature varies, then, for example, polarization changes, and then it creates a voltage change there, which is actually compensated at the end with several ways, either leakage in material, or just compensated by ions from the space. So actually, it's just a variational effect. Now, if we have a detector, we can also, or we must also start with a thermal balance equation, which is actually very, very same here, and only apply that external current now would be, we just write external current as a variation of voltage over resistance, and then added charge created by the thermal variations here. And once we have it, apply harmonic signal analysis to find out that the thermal variations now will have no DC phenomena. So actually at DC it does not work. And there is like an optimum frequency range set by two time constants. One is a thermal. Now it's opposite, like in bolometers, the same thermal capacity, thermal mass and thermal capacity is actually showing that there you have a maximum phenomena, and then there is actually electrical tau, RC limitation of this, this sensor here. So the pyroelectric phenomena has a peak at the frequency, and then can be applied. Well, not peak, but some cutoff at low frequencies, cutoff, so band pass characteristics. There is also very rich family of phenomena, because technically it can be a primary axis. So then we have electrical signal, which is coming directly from thermal variations on thermal load of a crystal, or it can go via mechanics. So if we just change lattice constant, and due to that we have creating, so like piezoelectricity. So phenomena is actually in general very rich. Can be bit primary, secondary axis, and there are a lot of materials which do have pyroelectric properties, and having different primary and secondary coefficients just to create a total coefficient. And in some case, primary and secondary coefficient, well, not some case, but many cases, they go in opposite sides. and for non-ferroelectric materials go in the same direction. So they add. So pyroelectric and thermoelectric devices, actually those are among few devices which are employed by Institute of Standards. Both NIST and PDB use this phenomenon employs this phenomena to create standards of or standardized or calibrated detectors for this frequency, also for terahertz frequency range. One more thermal phenomena is just, now it's not a single crystal, but if we have a junction with two materials, then we can create a thermocouple. And an example of employment of thermocouple in the terahertz frequency range is done, for example, at the University of Siegen here, where actually 8 thermocouples or 8 antenna coupled thermocouples have been used here as a detector for 800 gigahertz radiation. And well, characterized NEPs are here. One thing what colleagues at that time actually made an assumption that if you create an array of devices, you would get better performance. And actually, in the end, they found out by making such a combined array, the performance is actually not better, but by square root of 8 worse than that of a single device. So that for single device, this phenomena gives something like 100 picowatt per square root hertz NEPs, and now square root of 8. So it's this few times worse system NEP. But in general, it is also pretty decent performance at those frequency range. So I would like now to approach to the Golay cell, one of the most, well, also widely used detector, also for terahertz frequency range, although it is the same as a bolometer phenomena, is in general frequency non-specific to any frequencies, and only can depends on what is the frequency absorption properties of absorber. And in this case here, if absorbing film is placed in a cavity, well, we have window here, then we have a cavity with so-called pneumatic chamber with some absorber film. And then, so then the power comes here in, it heats the gas in the pneumatic chamber. And by this, we have a flexible mirror. The gas expands and pushes that flexible mirror. And just to avoid breaking of that mirror, there is a leak with additional ballasting reservoir. On the other side, this position of flexible mirror or variations in a variation in position of that mirror are measured by any other mechanism, like having light source, focusing on the mirror, and measuring the fluctuations with light sensor. So that's the general principle of Golay cell-based detector. And also one thing is that the gas or the special pressure that we apply has to go out of it. And one of the experiences just accumulated over years, don't leave it just on the window where sun can come in and heat. Once anything from outside heats your device there, doesn't matter, is it on, is it exposed to beam or not. If you just expose some temperatures, too strong temperature variation of the pneumatic chamber, either absorbing film or okay, so mostly absorbing film can break, and then it creates the damage of the device. So therefore, this is where just to avoid this absorbing film or just this pneumatic chamber to be destroyed by just too big variations. So it doesn't matter if you switch it on or off, you cannot protect. You have to protect it against too big thermal load. But The Golay cell also, like in the original paper of Golay in 49, can be very nicely simulated or just simplified to that picture. We have window, we have absorbing membrane with both thermal capacity, and then we have a change of the gas here, where delta P change of a pressure, which is proportional to change of a temperature. And the same thermodynamic picture has an electrical analogy. One can write it very simply that we have thermal variations like a source here, like a current source. We have thermal conductance, we have capacitance, thermal capacitance, and then we have thermal conductance of the gas connected to different types of capacitances, different points here, especially one of that is thermal conductance of the leak. So if one takes that and then converts mechanical or this pneumatic energy and then to absorb energy, calculates the changes, calculates just taking this simplified picture, we can come, or Golay even at this time came to the point that such a principle operating normal conditions has a minimum NEP of 5 picowatt per square root of hertz. So that's also very decent value, because just to remind you, commercial bolometers, helium-cooled bolometers have something like 3 picowatts per square root hertz optical performance. So we start here with 5 picowatts, so optimum, maximally available, land with something like 100, 150 picowatts for real devices, which is still very reasonable performance for those frequencies, well, for detection at terahertz frequency range. Now, pneumatic on micro machine. So it is now actually there is a big variety of devices where pneumatic and micro machine and sensors implement very similar cavities, and variations are measured now not by optical signal like in Golay cell, but by electrical variation by different ways. So one can just check like voltage created by bending of a membrane, and there are many ways how it is implemented. It has same limits like thermal limits, enthalpy fluctuations, which I addressed in very beginning for bolometers, and there are different ways just to how to get the ultimate sensitivity of variations that one gets, or NEPs, and actually one can create a big variety of microbolometer cameras. The principle is more applied to infrared frequency range, where wavelength is shorter, because in the terahertz frequency range now we have much longer wavelength, and the main question or the main challenge in the terahertz frequency range is actually the principle of absorption. Do we make it the absorption good or not? And this is where major or microbolometer cameras, if you know, like created by Leti in France or by Canadians, you know, and NEC in Japan. So they were kind of optimizing my microbolometers to bring them into terahertz frequency range as well. So same is also for pneumatic or micro machine sensing. And by this, I would like now to go to leave the thermal sensing and come to rectification. And would like to start the story of rectification by the statement, which is actually very old. I found it of one of application notes and at HP for HP application notes about diodes, with the saying that, well, almost every diode is a zero biased rectifier. So I would like to tell you how does it come? So if we just take Schottky equation, which is this standard exponential change of the current showed here by this type of characteristic, where we have saturation current come across the zero, and then this exponential branch above. And we bring a device into some operational point here. So if we have some bias point where we would like to just, okay, the statement is about zero biasing, but now in a general analysis, we just, let's say we have voltage, any additional DC voltage, like our operational point, plus a small variation of voltage, which we will apply somehow electrically on a device. Now let's do Taylor expansions of the current oscillations here to find out that we have a DC part and then oscillating part, and then in additional second term, order term to variation of voltage that would be rectified part, and so on. One can go to the higher orders of variation. So that is DC. This part is direct response, which allows us to get differential or small signal resistance, same as a slope of load curve or IV curve. So that's a resistance that we have, and then we have rectified current is the DC current that we had without applying AC signal versus this additional term that we have. So from differential resistance, we can get what AC power did we apply on our device. And from rectified current, we had this ratio. If we just divide rectified current over power we applied, we find that we have current responsivity, which is Q to N. Well, this is non-ideality of exponential dependence, K Boltzmann T. And at room temperature, it's about having N equals 1 is about 20 amperes per watt. Almost doesn't matter at which point we are here. We can be at 0 point, we can be at a very different, as long we trust the Schottky equation. For a diode, we would get this characteristic. So what does it make? Well, that difference. And the main point is impedance, actually. Our main question is how efficiently we bring power into that device. We did not say. So once power is on a device, on a terminal of device, then like every bolometer is frequency independent, so also every diode is a zero bias diode. Now, as I said, impedance is a key point. And if we would start with a PN diode, and we would say also same Schottky equation, but we have differential resistance, which we discussed before. Well, we have additional contact resistance here. There is one, we have junction capacitance. So at frequency high enough, the current would start not flowing directly through our differential resistance, but will be shunted by the capacitance of a junction. And for PN junction, for PN diode is also a very important phenomenon that it is transport of minority carriers. So there is a diffusive capacitance. So capacitance must, the carriers must diffuse through the from the region where there are minority carriers. So that's only diffusion transport, and therefore there is additional term which actually electrically can be very nicely comprised into this term of differential diffusion capacitance. And well, that's just junction capacitance, that's diffusive capacitance directly. And there is a differential capacitance coming out of IV characteristic. So we do that, and we find out that PN diodes, just due to those two big capacitances, both here are not applicable, not in general applicable at terahertz frequency range. They are still very good, actually up to microwaves. But is really exploited there is a Schottky diode. Because Schottky diode is a junction between metal and semiconductor, and the carriers are once they tunnel through the junction, they transport is in in a region where we are majority carriers, so there are no loss of due to diffusion capacitance. Still, junction capacitance is one of the most important. So, and in a picture, electrical picture, is nothing else than the shunting capacitance here. And what it does, it makes impedance of the device, so real part of impedance lower. So real part of impedance is this without I here. This is the part which is actually dropping here on RD, or it becomes with a frequency lower and lower. It drops down to the frequency after RT CJ becomes comparable to omega. So with that actually is not a cutoff frequency. Cutoff frequency is set where we actually start losing power at all on a serious resistance there. But the roll-off of impedance starts there already where RDCJ becomes, well, tau set by RG becomes equal 1 to omega, 1 over omega. So in a Schottky diodes, there is additional phenomena or going to higher frequency and then pushing limits of the frequency even more and more above that microwave frequency range. One has to take into account that the junction becomes, so we start for losing that 3D character of the transport, and it becomes more and more related to the surface. So so-called skin effect impedance. That's bulk spreading impedance, and then, well, barrier what comes in. So all those phenomena makes a roll-off even worse than that simple picture here. This would allow actually to operate pretty far in frequencies, but there is an additional skin effect and losing of 3D transport characteristics. Stops the operation of Schottky diodes. And okay, still have some time. Would like now to introduce one of the newest phenomena is or application of field effect transistors to detect terahertz radiation. And it's a bit of surprising topic there because actually over years it was kind of a consensus that Schottky diodes are the best diodes there. Okay, there are some others as well, but Schottky diodes were kind of the leading or most developed concept. And it came by theoretical works, first of all, prediction set by Diakonov and Schur in '96, analyzing very simplified transport equations of field effect transistor and actually looking not for detection. Well, '96 is a detection paper, but it started from the work in '93 where we looked for a plasma wave, formation of plasma wave, and actually their implication to the operation of device. So the physics here is very nicely comprised by two fundamental equations, or actually very simplified fundamental equations, charge continuity equation and the transport equation. So one can write transport equation in very different forms. This is just written originally used by Diakonov and Schur just to velocity. And electrical engineering, this transport equation is mostly written for a current, which is a product of N and V, but it has absolutely identical as long as it's correctly written. What we don't have here, there is no diffusion terms, they are omitted. And also in this very simplified analysis, also higher moment like energy transport is also not considered at all. But for the simple picture to outline the key or not key, but one of the type of performance which is important for devices going above their frequency, the cutoff frequency for transistors, FTs. So now for vertical, one can just do also very simplified charge density dependence on voltage. And this is true only for strong inversion regime. In general case, it is just a function of voltage. So one can just take this functional dependency and work with it. So one once has actually intrinsic. So intrinsically, transistor is nothing else than this. I would like to show that it's nothing else than a distributed picture. One can really very nicely to write as a distributed R of a channel, C, just C to the gate, and then there is a kinetic inductance, which also comes to be important at frequencies above FT. In addition, we have all parasitic elements here, and we have also to take antenna, some antenna having some impedance here, just for simplicity, that I have DC block here that we not let DC signal to get out here, and then we had it here to measure created voltage or current difference, depending on what we will read. So this picture is actually very simplified, can be described here as we have a distributed line, and then every distributed line here, has a characteristic impedance. If we go to frequencies large enough or high enough, where this characteristic impedance starts to be important, and this characteristic impedance has actually standard for electrical engineers formula. One can write it directly via distributed elements, resistance per unit length, kinetic inductance per unit length, conductance of the electric per unit length, and the capacitance of the electric, same per unit length. So those elements here are just coming directly out of the simplified analysis I showed on the even Yakonov-Shua analysis. And although that simplicity, there are still a lot of theories, especially devoted for transistor operation. And as an example can be, you can see a number of them developed over years. What is important that, actually the just transmission line theory is something like written by Oliver Heaviside in 1880s. And there is really a very practical side of that description, that technically, if you now understand physics or you trust physics, that simplified one coming from distributed transmission analysis or just simplified hydrodynamics, and then you apply from our other side knowledge of antennas, you can very well get coupling from external, from free space into antenna, into device, and analyze what is the performance of such devices, what is the best performance, or what both electrical, and then how can it operate as a device. And so what is very important now for rectification, or originally it was used that look how the voltage oscillations would appear if we start oscillating of RF voltage as an equivalent voltage source. Same voltage equations, created delta volt can be measured as a current, change in the current, and it is just very directly linked to, well, DC current is very directly linked to the created voltage and DC resistance or quasi-stationary resistance of drain to channel. And so in a limit of overdamped plasmons, where that's an example. If we apply a field, and this is like was shown in Yakonov-Shua simulation, so we apply voltage and we'll apply here like voltage source, we would create a plasma wave running out of source side into the channel, going to the drain, and then it would create also rectified voltage change here. So the term of overdamped plasmon is that this plasmon, although you have several wavelengths fitting in the channel, it actually decays so fast that it does not reflect. There is no substantial reflection from the end. this is the case where was not the most interesting one both for Dyakonov and Shor, and actually they left not too big attention there. They looked more into the wave phenomena and the resonances of them. But I would like to show there are several ways, like transistor can be applied, since we have 3 terminals, we can apply in the 3 different cases, or let's say 2 different cases. We can apply gate voltage here, but RF signal directly on the drain. In this case, we would shoot plasma wave into from another direction of the channel. Or we can have the same case, but now apply also short, this shunt here. So there are several ways how one can create waves. Those 3 scenarios. So first of all, scenario of Dyakonov and Shor showed here that there will be no rectified or this factor, efficiency factor here, created voltage at low frequencies. And suddenly it would appear at very high frequencies where actually where a plasma start form. This is about close to the cutoff frequency, or KL equals to a real part of KL(x1), where we have one wave entering into full length of a device. So for them, somehow it appeared that this is really high frequency phenomena, but it is enough to really see it in different way, just bias it slightly different to find out. But we have immediately rectified voltage here, which is so-called classic resistive self-mixing. So, and it is very well known that transistors are good rectifiers, although they are used, well, this is least application of transistor. Well, one would use it then for amplification in this frequency range. But so the key statement is that the phenomenon is actually was well known. What is not well known, or what was actually a big surprise, that it would go here. And even if a plasmon is really overdamped, it goes into some saturation here, which is for this efficiency factor is higher. So that was a big surprise. So that phenomena, intrinsic phenomena, is not ceasing with frequency, but it is actually slightly even improving. And now one can get to the quasi-static responsivity of it. And responsivity requires also to know how much power we would add here, but we can get out also power to apply from very same like it was used for Schottky diodes out of AC oscillations we applied, so from Joule heat. Now, I would like to tell that there is almost no difference which material system you would use, as long as you trust or you describe the same physics or same transport mechanism. So, and for this, those are conductivity curves of very different devices, like MOSFETs, aluminum gallium nitride HEMTs, or graphene FET, or CNT. If you use like this and then just calculate what would be current responsivity now, limited, well, we find that in a sub-threshold, there is some factor variation here. And this variation here is just non-ideality factor of the device. But we go slightly above the threshold, all performances are very, very similar, going to few amps per watt sensitivity. So by this, they all operate like diodes. Very same analysis what was applied to diodes. Actually, it doesn't matter now, do we have plasma waves or not? Actually, it brings very, very similar performance at a quasi-statics here to 20 amps per non-ideality factor. So it's only non-ideality factor of characteristics, which would make slight difference of a device. Now, above the threshold, all should look very, very same, except of difference in a material. So how well we control charge, or what is the nonlinearity of control, what is loss on excess regions, what are shunting capacitance, and so on. So only technical parameters. So this kind of puts everything under one hat, and I would love to actually, in the end, would like to say, no, everything is not so much under one hat, and physicists find a lot of interesting mechanisms there to outline. And those mechanisms actually are covered by the mechanism we skipped. What is the diffusion? What is energy transport there? So if one would add it or include the energy transport, diffusion terms, one would find that there is a slight variation there, and even graphene FETs actually, although being not the best here, that's just realistic curve. I showed realistic conductivity here, which is actually limited a lot by parasitic access regions. Now they are improved. So if I would put some most recent data here, then it would really fit very close to each other. So on one side, graphene FET has those access regions, which was working as a parasitic element here, but due to very nice energy transport, was not described by Diakonov. Actually, they can operate even at frequencies much higher than terahertz, where other phenomena lose. So the plasma wave that I discussed here starts to lose with the frequency, but other phenomena are coming in. So that telling that in general for engineer actually makes not much difference, depends only to know more about parameters and technology you apply to make decent sensors, doesn't matter which technology it is. So I would like now to come back to the main point, well, one of the statement which I addressed by this nice inspiration of Diakonov and Schur. They said that plasma waves are actually a few new mechanism for future detectors which would suppress Schottky diodes. And then I gave a special analysis to that statement by just making the system or just plotting or solving the system as we had here, very similar configuration, which or exactly the same configuration was applied by Diakonov and Schur in the paper. Look for voltage response here, but in addition, you know, it was directly there, even in their work 96 or all others. So it's not only voltage response and this amazing factor of F that was analyzed there, like enhancement over quasi-static performance, but its voltage responsivity is important. Same analysis I told you for Schottky diodes. We have to see how much RF current is applied now, or not RF power is applied on device to produce that change. And the solution is given there directly because we have RF voltage, which we have to apply to create that change. And from a simulations, we get RF current. And in this case, well, in the complex world, we have to take complex conjugated term here to find out which power we need. And that's URF multiply IRF complex conjugated by 2. That's power we need to apply to create this voltage change, and this would be voltage responsivity. So let's take parameters relevant for aluminum gallium nitride hemmed. So those are already hemmed. This is hemmed. Those are already much faster carriers than that as for silicon. So waves would be not damped in a sense that there is a possibility to get really decent standing wave in a channel. And if you plot at a different how the gate, real part of gate impedance would depend on in impedance is this red curve. On a different, on a frequency at different gate bias points, one would find out that impedance changes a lot. And at gate bias equals 0, for example, here it gets really pronounced waves. So this is where one definitely expects seeing, okay, it is in a few terahertz frequency range, so not that practical, but for simulation, one definitely would expect seeing standing wave happening in a channel. So these plasmons that were first of all, well, not predicted, but outlined. Now, if one looks into what input power one has to apply, so this product here, one would see, oh, but actually input power would also vary. And it vary in the opposite sign. You would like to get that enhancement away. Enhancement here, you have to impedance, okay, impedance gets lower, you have to apply higher power. Impedance gets higher, you have to apply lower power here just to create, or it just gets less power. And then we check what would be now rectified voltage or responsivity here. We would find out, well, voltage is this factor F, the blue curve. So once we are at gate minus 1.2 here, then we see that's a quasi-static. This you remember for damped plasmons, and then this is when we have this undamped plasmon case in the Yakonov-Shua case, and one already expects to see some oscillations here. But if we get to different bias points, and now it is even above 0, go to 0.5, and we have huge enhancement here, factor of 7. And factor of thousands is possible if one would take material with higher mobility. But what is interesting, if we now check what would be responsivity, it is a red curve here. And instead of voltage, I take current responsivity to show the difference between quasi-static current responsivity. We would find out that actually current responsivity now is not the same as this factor of 2 or factor of 3 now here increase. Actually, it stays more or less constant with very small variations here coming due to those standing waves. When we go to different bias points where these standing waves are very, very pronounced, we get actually that quasi-static responsivity is not increasing at all at this maximum. And the explanation is very simple. To create this maximum, you have to apply much more power. So everything would cancel. There will be still oscillatory behavior here, which is actually recently observed in graphene transistors. So when one sees, one can have this kind of plasmonic feature there, but it's not exactly related to this huge enhancements, which was predicted there. And in general, that's physics of unmatched transmission line. So that's a message there, which I would like to leave. Is, well, that enhancement factor, what was predicted, has just a little influence on detector performance. And nevertheless, that's really, this is what I would like now to outline very, very strongly. That's a very nice phenomenon. So even if it is not a factor 1,000 better as Schottky, that it was predicted in '96, it's still something which provides new tools, new possibilities to create devices for a terahertz frequency range where were not existing before. And this is what I would like to address after I am addressing challenges. That's a very, very general challenges, does not matter now which phenomena we are talking, is how do we actually measure experimentally responsivity or NEP of our device. And if we would now address to the case A, this is standard for microwave people or radar-based people. So one has a lot of power, usually you don't care so much. So, but you know, you have your antenna with directivity, you radiate into space, and then you have your receiver, which just sees with some specific directivity angle, some cone of radiation can take from a space, and you have this distance here. So it's so-called transmitter, Friis equation for transmitter and receiver for radiation of antennas. Such a case, it's hardly imaginable in the terahertz frequency range. We don't have that much power. Once we spread it in a space, we travel long enough distance, actually very little is coming here. But that's one way how to characterize what would be your device, your receiver, your detector. If you have your source with well-known characteristics of emission, you have your receiver with well-known characteristics of receiving, then you can get it. You can get estimation of power intensity you have here and effective area of your receiver or detector here. The same thing with reflective area. Instead of having antenna like Hor antenna here, you can just put a detector array sometimes. And you also ask yourself how to define the effective area of such array. Or if you have single device, how to define effective. And there are several ways. So one is, antenna gain. So you have to have antenna gain, which is actually also loss of it. It's just not only directivity of it, but also power loss on antenna. And this is how you define. By this, you know how much power really comes to the point based on the best of knowledge coming out of antenna research. So you can define by maximum directivity. So maximum directivity is also related to antenna gain. So it's also dependent on the very same equation here. But now in this case, we have more power because we say the power is here. We don't include the loss which we have here due to antenna element in addition. For a B type of, then we don't use such a kind of horns and would look like this. It's actually very similar, like also like in the first case. We can see what would be the physical area. And this is where even myself at the very beginning in 2007 made a mistake saying that physical area probably is the area of metal. This is where actually people coming from material science also forget a lot, saying we have a very beautiful material which is 10 by 10 microns because it is just a flake or just really, but we applied antenna, but we say our material size is that physical area. So this physical area is one of the biggest misconceptions, except of one can take that physical area if one properly calculates as a pitch of a device is here, pitch between detector arrays. So could be that correct. This would be the only correct estimate of the physical area. But otherwise, just saying that that's area of material or whatever would be wrong. One is instructed better go to antenna physics and just look what is effective area of antenna that you use here. One of the also very big misconceptions which came in and actually lives until now using diffraction limited spot area has nothing to do, but somehow physicists like it so much that actually applied the formula to characterize what could be effective area of your device by lambda squared over 4. And you would find out coming from antenna people, they say the area of omnidirectional antenna. So although this is now coming, relies on the knowledge of antennas, it even gives the pi times smaller area, as I said, that of a wrongly taken area of diffraction limited. But this one tells already that you know about your antenna, so actually you can calculate back. The gain should be given, so you should be able to calculate back to the effective area and kind of cross-check it. There is one very special case where we say no normalization. And that's actually, if we come back to what is an EP, if you find on the data spec sheets of bolometer, spec sheets of commercial pyroelectric or commercial Golay cell, and that's usually, you say how much power you had in the beam and you bring to the device. One of example is if you use two lenses here and focus and then say, I just measure it, the power what was here, or maybe with some loss of the lens, but power what was here in a free space, and then it is on the detector. And that's the only proper comparison of optical performance to commercial devices. And this is seldom done because typically scientists, when we create our devices, we know that we lose so much, and then we say, actually either based on antenna gain or just based on a detector area here, and mixes that if you would do the same to the bolometers, to Schottky, even to bolometers, to pyroelectric or Golay cells, then the powers would be 10 times or more better. NEPs would be lower by factors of 10. So commercial devices on spec sheets typically give correct optical performance, which is in the picowatt per square inch, few picowatts for helium-cooled bolometers. But if one does it without a comparison here, so that's one case which is often used, and then when we do no normalization, we say, okay, we have that much power in the beam, and this is what we would measure with our device if we would apply proper optics. So those are challenges, and it's pretty, it's not straightforward in many cases, especially if you get if you are so excited having very beautiful material in your hands, you know, you would not get it, like a carbon nanotube device, which lives just very short, so you don't have that luxury to do too many experiments and to investigate it using full knowledge of microwave generated by microwave people or antenna people. But I would like now to give a summary where we are with FET-based devices, and just a small, just showing you a few things. Just a summary of few families of devices created at different frequencies. So if we had all the technology here, we came to some best performance at around 600 gigahertz, and we deteriorated, and we changed to the 90 nanometer process. By now we are at 65 nanometer process, and everything become better and better. And actually, the statement here is that such devices with this performance are not only competitors to Schottky diodes, but we really believe, or my colleagues who work with me believe, that we already outperforming Schottky diode detectors above 1 terahertz. So this is really one of the technology which started probably with not best scientific insight on the performance, but with the effort placed there, we come to the performances which are really outperforming or setting the state of the art. And so in a cooperation with different teams, we have created practical applications. Well, this is how approximately how one device would look like. So if one has spiral antenna, just it placed on a hyperhemispherical lens, and then, well, radiation couples from the substrate side. This is the most usual case to couple radiation efficiently out of free space into a device. The sizes here are absolutely not comparable, because antenna would be really below a millimeter there, with the lens being tens of millimeters. So the diameter would be 12 millimeter usual. But it just shows that such devices are really capable of many things in the different applications, like sensitivity for a passive radiation, hyperspectral imaging using electro-optical dual comms, or just directly for SNOM experiments, for near field, high resolution near field optical microscopy. So same that has been done with standard Schottky diodes, standard sources, also now can be done with field-effect-transistor based devices. I would like to outline a few performances here, and one of it is just, we did really, well, as you saw, the number of devices, and we apply for imaging or detection of the photomixer radiation. That's optical photomixer, and for example, this performance shown for 90 nanometer CMOS, now for 65 nanometer CMOS, we have even slightly better performance there. And you can have decent detection up to the maximum frequency operation. And actually, you can also measure beam profile here. So even if you do not measure whole power, because the detector effective area is pretty small, and you can use it really to map area at very different frequencies. And this is measured at very different frequencies, and for example, measured effective area of focused photomixer radiation here, actually up to 2.6 terahertz. Now it was if a patch receives only a fraction of the power, but the same antenna coupling, or one can think about antenna as being set from combined antenna we implement directly on a chip, and antenna, well, lens antenna. So this is usual term in microwaves. So it is placed on a superstrut here. And once we do this, we can compare our best performance, broadband devices, and that's actually performances of broadband devices here, but we can measure also down to the functioning range frequency, function range of the photomixer. If we now use patches, as I showed there, with improved coupling, better focusing, then we get exceed performance by almost the order of magnitude here of a broadband device. This was expected, and actually it's also very nice implementation towards future frequency resolved systems. And one unique example which we are working right now is since we have the possibility to make arrays, not a single device. That's how a single patch would look like in a very standard CMOS technology. But you see here in the center is the patch. So this is receiving antenna. Well, we cannot see transistor, which is submicron. The patch here is already something like 13 by 13 microns or 10 by 10 microns. We also see a lot of those bumps, and that's actually metals that we have to include in a standard, like as a requirement, a standard fabrication technology. But so this is this rough surface that we see here, but in the center, one can create really big arrays of devices. So one can think about cameras, or one can think about using conglomerates of antenna to increase effective area, to reduce reflection loss and so on, reflection signals, and improve on applicability of those devices. And one of the very interesting result until it was measured by colleagues at the Leeds University is transmission spectroscopy of methanol gas from a gas cartridge placed at some pressure, at some lower than atmospheric pressure, for sure, because gas lines become narrow only at some millibars, a few millibars. But what is important? So if QCL is used here now for transmission, and then QCL frequency is shifted by the current, by operation point, and this can be done with very fast shift, you can very nicely measure absorption spectra of methanol gas. And just to tell a statement there, a strong statement that we have bolometers for many decades developed. Such a measurement was impossible with bolometer. It's not about NEP, it is about the frequency of response, how fast the device is, and how well this is resolved. So this is one of the nice examples there. And actually, one can go more towards time-resolved tracking of chemical reactions via terahertz spectroscopy. This is something that we are really looking forward. Probably the last important point, or very interesting point about those transistor-based devices or IC, because it is IC technology, very standard IC technology, which we exploited here to create detectors, state-of-the-art detectors for terahertz frequency range. It's also what would happen if we would load something on the antenna itself. And first started as a very interesting mind exercise. What would happen? Let us simulate. Let us make an experiment. And we found out that actually there is a huge sensitivity to antenna. Once we change, load it somehow by the electric here, then we change properties of that very small area of the antenna itself. And that's really area which can be taken down to something like 4 by 4 or 10 by 10 microns, even for wavelengths which are on a millimeter length. And so that's really a nice tool to have near field sensitivity. In addition, IC technologies allow not to implement single sensors as I showed there, as detector patch or whatever, but actually use varieties of it. So have a 3D implementations of different types of coupled structures. So this is, for example, meta surface placed below the detector here. And since we have it electrically, we understand antenna. Well, I can write antenna as electrical equivalent. We know detector also as electrical equivalent here. It can measure variations of now appearing due to the near field load, which appears on the equivalent resistance of antenna, or for example, equivalent capacitance of antenna. So those can be altered, especially capacitance as resistance as well. But and then we can measure detector as near field sensor. So started as a fun mind experiment. We also implemented structures here like coupling structures, and then enhanced meta surface, like a 3D meta surfaces as well, to find out that, well, that's a concept of it, but in the general, you can use any external terahertz sources like photomixer or VDI, and then use detector with loaded, or we can use actually as small as possible. Another part of discussion would be CMOS sources for terahertz. So one can do the systems which are now extremely small and pretty capable of near field sensing. And as an example, the detector normal response would be this black curve in the frequency measured with photomixer radiation there. And if we load with ethanol, for example, poor drop of ethanol, then we see that the resonance shifts like that, because epsilon, ethanol has very little loss, so it's only dielectric load that we have on antenna, nicely observed. But if we apply water, that both things, we see dielectric load plus loss of the which we have in the water. So as a polar liquid. So and this everything can be measured directly by the response of the detector as well. And if we compare where such detectors are with the state-of-the-art done in terahertz for biosensing, those are mostly those open dots there. Established bioanalytic tools would say that one has to be able to measure those concentrations. Then our data, which we made on our sensors, is really the top edge of terahertz sensors here. So with some potential, well, there is some need also to improve it, but it shows you the big improvement here from free space measurements going to near field measurements. Actually, those points are also near field measurements now. Then one can load the sensor or detector with some bio sample there. One can improve sensitivities actually to the top edge of what has been achieved by other groups using very commercial tools, or well, developed meta surface tools as well. Now I would like to stop talking about this room temperature sensing and terahertz detection. Would like to address the last point: what has to be done to push up or go to the maximum sensitivities? And is it possible to be able to detect 4 single terahertz photons? And the answer is yes, such devices do exist. They do have strong interest. And one of an example is developed by, I think it's Caltech group, or just cooperation for GPL Caltech. It is based on a hot electron bolometry. So if one has NS transition here. So you see there on the picture, it is very important, big question, how do we couple radiation? So it is all the topic. I did not address it in a very, very detail, but this is far infrared antenna. So what do we use as absorber? Usually TAS or SNS structures are so small, like transistors or like diodes are so small, they do not see the radiation directly. The antenna brings radiation on the device. So this is where power estimation, antenna coupling, impedance matching antenna to the element is a crucial point. But to that, knowing this is also important, what is the physical phenomena bringing us to this most important enhanced sensitivities. So one phenomena would be having transition edge superconductor placed between two really superconducting states. And that would create, in this case, would be normal material, and here would create some gap in the material, just made by superconducting. But once we have this gap, so normal transport is not so easy possible, but so this material isn't resistive, but the transport here is still, there is a nice, well, physical description how the carriers can move out from here into it, so-called Andreev reflection. So it just tells that it is possible also to transfer current from normal state into superconductor state, and actually in both ways. And that could be used as a, well, electrical thermometer, looking for the change of a temperature here, or exploiting sharp temperature, TCR, temperature coefficient of resistances here. So once we employ that, also very same way, using silicon lens or substrate lens coupling into that antenna device, and this antenna is actually, you see, complicated antenna, not the most simple one. But once one does it, one can just get a statistic of counts. And so detector noise itself is here. And then one applies terahertz radiation, one gets statistic of counts when it shifts slightly, shift in the noise peak there, and also peak appearing here, showing that now such device is capable, actually cooled below Kelvin. It is capable of measuring photons. And yeah, so if that would be absorber coupled, that would be this, but then antenna coupled also can extend it. So absorbers do typically work only to tens of micrometer wavelengths. Then with antenna, one can extend it much further into this terahertz frequency range. There is another idea which is pretty interesting to approach photon sensitivities, is to have a photoconductive detector. So once we have a photoconductive detector, the photon excites here electron hole pair. And then this is the current which is measured. So in this case, there is no gain here. So actually gain is usually below 1 because one photon creates just one electron. But a quantum dot single photon detector is based like this. So let us have a charge sensitive device, well, a channel here, like this is like field effect transistor, where we do have current flowing through a channel. And then once we create now photon, not directly in the material here, but in a gate material here. So the photon excites carriers here, so excites additional charge, which modulates current flowing here. And actually this provides the scheme to get gains. Quantum efficiency is higher than unity. So it is like amplifier phenomenon there, or amplification of carriers. How can it be done? This quantum photon detector, this is also, well, typically known gallium arsenide, aluminum gallium arsenide heterojunctions. And one can use a Landau, so one can create a quantum dot in by two things, by depleting carriers here, going to very low temperatures, one thing, depleting carriers, creating quantum dot, and then adding magnetic field to create splitting of Landau states. And then allowing current to flow very good if the carriers are now in the second Landau state, while they are immobilized if they are in the first Landau state. So once we increment that scheme, so for example, here the detector of Komiyama made in Tokyo University is optimized just by antennas here in a frequency range close to, so it's 275, so it is slightly above 1 terahertz, nearly from 1 to 2 terahertz frequency range. And an example of their device is shown here. Also, a good device is okay, so let's start from antenna, so from e-picture here. So that's a nanofabrication. One has to do it really sub-micron fabrication here to be able to create a quantum hole. One has to cool it down to sub-Kelvin. In this case, it was 300 millikelvin temperature. One has to apply also large magnetic field here in this 5,45 Tesla. But so that's an antenna here, optimized, defining frequency range of operation as well, or absorbing of the photons. And then it should be placed in a terahertz waveguide. So it is also substrate length here, and then terahertz wave comes here through a waveguide into that cryostat. So this is an example of the built-in crystal there. And now if one would look, now let us change gate bias voltage and see the conductance of the structure, then this would be the dark characteristic. And once we apply terahertz radiation, we can see this what is reported, or one can see that this characteristic changes here right now with the spontaneous events here, where single photon counts are happening. So that allows also to create quantum sensors now based on a different principle. So it's not necessarily hot carrier phenomena, but quantum dot based phenomena, and employing the gain or multiplication of the current by the charge stored in a quantum dot. So I would like now to stop the lecture here by giving a summary. I run, well, pretty broadly described fraction of existing methods and developed techniques for terahertz detection. And would like also to tell that, well, it is definitely a field which is perfectioned over many decades. But for example, like a field effect transistor, nice development in field shows that there is still a room and demand for novelties and improvements.
Stop. Thank you for your great lecture. I think now it's time for the questions. So if you could turn on your Q&A panel below, right next to sharing screen. We have 3 questions so far, and I'm hoping our participants have many more to ask. Okay, so I see 3 questions, and very first one is why silicon lens, but not germanium or similar? That's a good question. Since most of the case use silicon, so I don't know which it was 1040. So we have to find out for which question. So silicon is the mostly developed material where we have very good quality, so low loss. For example, there is a very different optical quality silicon or ER silicon or terahertz, and that's not the same. It's only, you know, float zone silicon, very special, very impurity pure silicon, which we use for terahertz frequency range. So I would say, why not other materials? Because there is so much effort set to make silicon nice. So there is a availability of it. And
And because polishing should be very similar to that, but the quality of material, I think, prefers silicon to others. And silicon is not equal to silicon. Then you buy silicon to make your lenses, or you buy silicon lens. Be careful. Do you buy ER grade or Terahertz grade? And that's a huge difference. I hope I responded to this question. If not, please. Okay.
They will follow up if it's not enough.
Yes.
Oh, yeah,
so
we go.
another question is, what is response time of Terahertz FET and quantum dot photodetector? So about TeraFETs. So response time of a TeraFET. So technically, it can be as fast as a pulse of terahertz, so single cycle. Can be. And we did efforts there to show that physical phenomena of rectification inside is fast. Now, if you create electrical device to give to your colleagues or users, you always ask what is RC constant of it, or So no, there is one thing. Once you have abundance of the power, you can use photodiodes actually for telecommunications. So photodiodes with large resistance, it can be used in the current mode, and you can get it to extract. But the question is a SNR, would you get the same SNR or not? So if you talk about role of SNR of your device, it is pretty very well linked to that RC time constant. And now if we have R of 1 kilo ohm of our device, typically, and actually it is not one, it is typically larger. And even smallest Cs of our amplifiers limits it to tens of megahertz. So it is very easy to make best stated SNR or NEP devices below 10 megahertz. And the challenge to make into video requires you to make impedance transformation to 50 ohms or whatever. And this is very, so let's say physically, it is not limited. Practically, it is limited a lot by your readout and by your application. Now, quantum dot photodetector, it is also very same. It is just current flowing, how fast it is, and how fast the changes are. So in general, this is very same concept, and would end into very same limitations. Once you have large impedance, you cannot read it fast, unless you make transimpedance amplifiers. Well, you implement that thing, but then you have a noise coming additional due to current and so on. So it can be fast, but it would not give you the same SNR. And I would like to say, to add to this, the same with pyroelectric detectors. So pyroelectrics are not that slow like Golay cells, not 20 hertz. So typically we have with Golay cells, runs into hundreds of kilohertz, no, hundreds of hertz. But if you know your application, if you need just to get a really fast response, you can change impedance of not your amplifier, but you shunt your device with a much lower impedance, and suddenly you expand your bandwidth. You can measure your pulses down to, I don't remember, but nanoseconds would be, well, would be maybe bold statement from my side, but you can really measure very short pulses. Again, on the cost of the power you apply. So your sensitivity is dropping down, but like a pyroelectric phenomena is just RC limited. And by that, you can measure, optimize your readout and get really fast processes. Okay, the question by Martin, what is material of terahertz waveguide? So which waveguide? This is Komiyama probably. So typically, terahertz waveguides, it is a very special technology to apply or to bring radiation into terahertz cryostat. Well, into cryostat with a special terahertz windows with magnetic field. Usually those are tubes
but actually, I know that the Polish groups, actually Warsaw is extremely experienced there, so I could just direct you with Jerzy Lusakowski group just to ask them more or less. I think those are details from them. I'm just in this case have academic interest to see there, but never built this waveguide running to sub-Kelvin temperatures by myself. So sorry.
Okay. Are there any more questions that we'd like to ask Alvydas? Well, okay. If not, well, thank you once more for this amazing lecture. And next week, we will reconvene to see Professor Wojciech Knap, who will tell us about plasmons for terahertz radiation and detectors, filters, and amplifiers. Okay, thank you again.
Okay. So
for a
thank the
brilliant
audience
lecture.
and have fun with new lectures or your studies.
You're of course welcome to join if you'd like. Thank you all.
And thank
have
you
a nice-
organizers for giving this opportunity to address, to present the
Thank you.
topic of terahertz detectors.
Yeah.
Thank you. We appreciate.
Thank you.
Very much.
Yeah, good then.
Okay.
Bye bye.
Bye bye. Have a great day, everyone. Bye bye.
Bye.